Hey, welcome back. Today we'll discuss the cosine Fourier transform because I find that is a fundamental transform, and it's not very clear where that pair comes from exactly. So, why Fourier transform of cosine is pi square brackets delta omega minus omega 0 plus delta omega plus omega 0. Let's start from very far. First step back, Euler identity, which is exponential function raised to jx cosine x plus j sine x. Why is that? Let's take the series expansion of sine, cosine, and e raised to x. Sine x as that expression, cosine of x as that expression, and ex as that expression. If we now multiply the exponential function series by j, we obtain this expression, and becomes this 1 because j squared, of course, is minus 1. And we rearrange the terms so that the blue ones are exactly the cosine, and the red ones are exactly the sine multiplied by j. Hence, the formula of Euler identity, e jx cosine x plus j sine x. So now we can say that the e jx cosine x plus j sine x and e minus or negative jx is cosine x minus j sine x. So then we add and subtract these formulas reciprocally, and we obtain, if we add them one another, the expression that you can see, and finally an expression for cosine with exponential function. A similar result is obtained subtracting the two formulas, and we obtain an expression for sine with exponential function. Dirac delta. So now let's consider the second step. Dirac delta is defined as follows. Delta is equal to 0 everywhere except for t equal to 0. The area of delta is 1 because delta is has width epsilon, as a height 1 over epsilon. So if you multiply one for the other, obtain 1 as area, and so the integral is equal to 1. And above all, delta has the shifting property, which is the integral of a function multiplied by delta as the effect of extract the value of the function in that point t0. So remember, above all, this shifting property. Then let's compute the Fourier transform of cosine. Cosine j omega, the Fourier transform of cosine, is the integral of cosine omega 0 t times e minus j omega t. And then we can substitute the expression we saw in the previous slides, and we end up with this integral expression that is not absolutely not trivial to compute. So good luck with those integrals. So what can we do? Here comes the genius of Adam Panagos, or Panagos, whom I give full credit for this splendid explanation, and I thank him. So Adam, if you see this video, thank you for your explanation that saved me during my studies. So if we are not lucky going with direct Fourier transform, we can try the reverse Fourier transform. So we are in this situation. Cosine of omega 0 t is equal, the expression with the exponentials, is equal, by definition of Fourier transform, 1 over 2 pi integral of an unknown function in the frequency domain, e j omega t d omega. Remember the shifting property and look at the similarity indicated by the arrows. You can see the two boxes, and you can have the idea that e j omega 0 t is a sample of the function e j omega t sampled in omega 0. So somehow we can imagine that a delta has shifted the exponential function in omega equals to omega 0. Hence, the same expression, we can write a delta function both for the positive exponential and the negative exponential, and then insert a pi to cancel the one given by the integral. Hence, finally, we have the pair cosine omega 0 t in time domain as the Fourier transform pi square brackets delta omega minus omega 0 plus delta omega plus omega 0. And we are done. Feel free to comment or contact me, and because we are on YouTube, please subscribe and click on the notification bell to receive updates on ideas I come up with. And consider to give a thumb up too. And share link or talk of this video with anyone that could be interested in this topic. And remember to check the video and channel of Adam. I will link in the description. So that's all for this video. Stay strong and see you next time.